Hello. So before diving into the food review project, we need first to have some working or maybe hello world projects regarding the PyTorch and understanding its structure. And then we will be going through another lecture which introduces GRU, LSTM, and RNNs and any recurrent neural network within PyTorch and how we can use it. After this, we will be going through another lecture which have this tokenizer of the Hugging Face and how to use it as a default tokenizer for the code review model. Then we will be building the whole SA or sentiment analysis model using such multiple lectures knowledge. Okay, so now let's start with the first project using PyTorch in order to go through the PyTorch template step by step. So as you can see here, this is image that have been shown before regarding the PyTorch structure. So today we'll be building each module from these through this lecture. Okay, while doing this, I'll be having this iris classification project, which is a simple data set which contains 4 features regarding the sepal length width and petal length and width. And the prediction is whether it is acetosa, versicolor, or virginica flower. Okay, so we need to classify regarding these features, what is the type of flower is it. Okay, so let's start. First, I will be importing the needed packages, like for example here, pandas and numpy for reading and pre-processing the data, and this is torch requirements. I need to import these regarding the data loader and the Adam with weight decay, which is an optimizer that we will be using as our optimizer. And this is the TQDM for just showing the progress of our looping in the training loop, and the train test split for splitting our dataset while training it and evaluating it the same way. So let's read our data. You can download this dataset from this link that I have added through this notebook. Okay, so as you can see here, this is the dataset that I have, and now we need to change the format of the label into integer. Okay, so we need to let's check first regarding this what is the types of indices. Okay, so we have iris virginica, iris salsa, and versicolor. So we need to encode each one of them. So I'll be using a simple encoder, which will be just a dictionary for giving them each of which an index. Okay, be a dictionary like this is a label and label index. Okay, for label index, label in. Okay, so now we have the dictionary, which in this index by 012, and this is the label dictionary. And now we're going to map the speeches as the speeches. Let's make it label. Okay, and this is the speeches dot map label dictionary. Okay, dot okay, so now we have this we have these 3 labels. As you can see, it's just a very small dataset, so don't care about the accuracy, because deep learning of course needs a huge dataset to be trained regarding its parameters, and like some research papers that we need 20 times the number of tokens in order to train 20 times the number of parameters. We need the dataset to be 20 times the number of parameters. So we have like a huge dataset, but currently we have a very small dataset, so it's toy project, but it's good to work around. Okay, so first thing, we need to have this dataset, and as you have discussed before, the dataset is nothing but just to pre-process anything within the data. So any type of pre-processing we need to do before ingesting our data into the model, we will be making it inside the dataset. Okay, any pre-processing, any changing in the color scale of the images, any tokenization of the words, of the reviews, of the question answering. So all of this will be taking place in this dataset class. Okay, so let's first start with the init. So what is the input of the dataset? It is of course the data frame. Okay, so let's decide what is the data frame that we will have, and the length will be of course the length of this data frame, and we'll be returning this length. And the get item will be returning, what is the objective of the get item? It will be returning a dictionary of input and output. Okay, let's call it output. Okay, so what is the input of our model? Our input is all of these features, right? So basically we need to I need to locate, for example, the fourth item and all the columns till the fourth column. Okay, now I have all these four features regarding this, for example, ninth record. So the ninth record, I need all the four features regarding this record. Okay, so the item here is the index of the record. So x will be df or self df dot I locate this item and take all these features. Okay, and the y will be dot ilog of item, and only what is the name of this feature of the label? It is label. Okay, so we need to add here label, but we need to remove this lock. Okay, to make it lock instead of ilog, because ilog takes an indices. Okay, so that's like that. And here we need to add torch.tensor because we need to convert this into tensor. Like for example here, the values, I don't need them to array, like I need them to be tensor. Okay. Okay, yeah. So something like this. I need to convert that to be something like this. This is the input of our model. So our model don't take any numpy or any list, it takes a tensor. Okay, and since it's a float, then we have to make it in a float way. So here we need to define the data type to be torch.float. And the output will be also a tensor of y. And this will be long, for example, but it will be auto-defined. Okay, so that's, for example, our dataset. Do we need any pre-processing? For now, we don't, but in the food review project, we need to tokenize this input. Okay, but currently we need only just to take the input and output and return them into tensor format. So for example, if I define a dataset here and give it the for example the first 5 records, and I take the first item I will have this dictionary which contains the input key and the output key, and the input will be this tensor and the output will be that tensor. Fine. So this is not the final way, but we need to make it in batches. That's what the data loader will do for us. So regarding the batches part, we will be discussing later. For example, like this is the data loader here. I can take it, for example, for you and give you some idea of it in the same way as you are developing it. So for example, I need to have this 100 and the batch size will be 5. Okay, and I need to shuffle this. Okay, so what does this mean? This means like instead of getting all our 100 records and putting them into the RAM, we are basically putting each 5 records into the RAM, pre-processing it, putting it to the model, giving the prediction, calculating the gradient, and then removing them and picking the next 5 records. Okay, so that's very efficient for huge data like images or something like text, huge text. So we cannot put all the Wikipedia data into the RAM. Okay, we need to break it in patches and save it and pre-process it, and then we make the prediction and backward propagation, etc. Anything within this certain patch, and then we get the output and update the model parameters. That's it. And get the other patch, update the model parameters, and remove this. So the main objective is to update the model parameters given this patch. So for example, here I can show you how we reprocess this. Okay. Let's make it false for this example here. Okay. I can take all the dataset, for example. Here, I think. Let's see if I reset the index. Okay, this might be happening for okay, because I need the input here shouldn't be the dataset, it shouldn't be the data frame. It should be, sorry, I need to compare it. It should be the dataset itself, okay, which is I had just pick it from here. So this will be the input to the data loader, not the data frame. Sorry for that. And here we'll be having this batch of 5, but for example here I need to make it 100 and then make it true. Okay, so here you can see this is a batch of 5 records, and this output also a batch of 5 labels, and it will be sending our prediction to the evaluating our model using this true output and giving this input. Okay, but let's remove this for now. Let's go to the model, and we'll be building a simple model for this. Like it will be just 3 layers with linear dense layers, and we will be predicting the output using the CrossEntropy loss function. So the CrossEntropy doesn't take any activation before it, doesn't need any softmax because it internally applies softmax. So let's start with building the model. Like I can build the first layer, a linear layer. Okay, so what is the input? It should be input dimension. It just takes the dimensions. Okay, So I need this input dimension, an integer, and also the output dimension. Also it's an, and let's define this, like for example 64, and then the second layer will be 64 and outputting like for example 128, and the third layer for example takes 128 and outputs. So the input of each layer is the output from the previous layer. Okay, and for example if I have here 256, I need to have another layer, and this layer will be 256 as input, and its output will be for example 16. So these are all hyperparameters. I can define a million of layers, but these are all hyperparameters that I can make. And the wider you make it, you can have an overfitting because your neurons have saved the data, didn't learn the pattern, but it's too small. Let's say that overfitting have occurred, or it didn't learn enough, so you might be decreasing or applying some overfitting, avoiding techniques like patch normalization or dropout. So but we will be taking it in a simple way. So for example I'll be having 3 layers. You can apply difference and see what is the best works in order to have a better accuracy. Okay, and the forward here will be should be returning the output or the predictions. Okay, so for example I need here like the input X is basically these 4 features that I have. Okay, so X will be a tensor, and I need to apply this, I need to propagate this input into these 3 layers. So I will be having this FC1 taking this X, and then I can break the output also in X and have maybe a ReLU applied for it. Like I can have this ReLU activation function. I might be doing it in this way or back to view, and then we might be applying also ReLU on the second activated layer, and the last one, it can also be a ReLU, but I will be leaving it as it is, and this will be the logits or the predictions, and we return these logits. Okay, so now let's be trying to defining our model. Okay, I'll be calling it IM or iris. Okay, let's call it model for now, and irisnet will take the input dimension will be 4 and the output dimension will be 3, which our dataset is about. So now we have defined this. If I have a GPU, then we need to make it on this device, which should be a CUDA or something. Okay, but we don't have a CUDA right here, so we have, but if you have a device, if you have a GPU, you can make it to CUDA example. We'll be discussing it more advanced later, but let's be working simple for now. Okay, so now I have the model initialized, so I need to have a synthesized dataset so I can make any random dataset which will be of size, like I need to make it for example 16 record, and each will be having 4 features. You can check the shape. Okay, 16 by 4, and then we can propagate this into our model and take the output. And the shape of the output, if you can pause here and predict what is the shape of the output we have. So basically, if I run it here, it will be 16 by 3 because 3 is the output value. Okay, so regarding this, I can, for example, look at this output. So it is three probabilities, you can say, for each label. Like I have three types of flowers, uh, Virginica and Stosa, etc. So these three types, I have the model predicts, giving such input, random input. It predicts what is the label of this given input. Okay, so this is the, you can see the probability of which record. Like for example here I can see that the second label is the best describing this. So if I need to calculate the accuracy here, I can use the label. For example, if I need to define the maximum value of this tensor, of this multidimension tensor, so I can use this argmax of dimension 1. 1 will be on each row. I will pick the maximum value and giving the index of the maximum value, which will be the label actually. So for example, here it should be returning 1, and here it should be also returning 1, because this is the maximum value across these three. And here, for example, it should returning 0, etc. So for example, yes, okay, so 1 1 0 1 0 1 0. Okay, of course it is random initialization of the parameters, but I'm just showing you how we can play with the tensors. Okay, also here we have another way of defining a network, which will be much compact and easier, but I will be showing you something other thing. Like for example, if I have any errors within this forward method, I can, for example, print here the x.shape and find it, for example, like after fc1 the shape will be, and here for example after fc2. So I can debug the code in the simple way of print statement. I can insert many, as much as I can, print statements inside the forward loop. Okay, so if I have defined this, so I can see like the input is 16 by 64. Now it is getting to this 64 and 28. So here I have 16 by 128. After this I have 128 by this output dimension. Okay, because I didn't rename it to logits. It should be 16 by 3, which is the output here. Okay, but we have a different way of defining these three linear layers. Also regarding these ReLU activation methods, it will be all in a single structure within this initialization of this module. So if I commented them and make it a sequential object. So what does sequential do? It takes a sequence of layers. So I need here a linear layer, and the input of it is the input dimension, and the output will be 64. And then I have two other layers, which will be 64 by 128 and 128 by output dimension. Okay, and what if I need to add the ReLU, etc., I can add them here. Okay, so in that case I can only have them all in that way, and I can remove all of these and rename this by net, for example self.net, and call it in this final output as self.net x, and let's run it again. Okay, it takes the same output, but the main drawback here that we cannot insert any print statements or any debugging. It will not be so easy but we can add something like called hooks, so it can be also added, but it's a little bit noisy, so we'll be covering it in a different lecture. Okay, so I'll be keeping this compact format for now. You can also add different layers other than ReLU, like you have uh, like, millions of layers here. Like for example, I can add patch norm 1D, one dimension, because I'm working with a one-dimensional data. Two-dimensional will be the image, okay, like the batch normalization, and this is the input of it is 128, which will be the output of the previous layer. So I can have this batch normalization also applied, and I can save it for now. And now let's work, and also I have this dropout and takes a probability, for example 0.3, like currently 30% of the neurons will be dropped randomly while doing the training, but while the prediction, all the neurons will be activated. Okay, so we have two modes, one is the training and one is the prediction. So while training, this dropout, this batch normalization will be activated, and it will be applying their effect, whatever they are. Like dropout will be dropping or cutting off the neurons, and the patch normalization will be normalizing any inputs before it gets to the next linear layer. And while evaluating, we will be changing the mode into eval. So what does eval do? It will be deactivating these two layers. So in that case, we will be only going linear, low, linear, and linear. So these uh, two layers will be deactivated in the evaluation mode. Okay, so that's an important point that we need to understand, because we'll be doing this while going through this engine module. Okay, the engine module here is this three methods here: the train, eval, and test. So the train will be the training mode, the eval will be the evaluating mode. Okay, so I've built the dataset and the model, so let's go to the engine part, and let's uncomment them. Okay. Okay, so this is a training function. It will be first of all doing this. The training function will be doing the forward and backward propagation of the batches. So it takes as input the batches from the data loader, as we have discussed earlier, the model, the optimizer, and the loss function. Okay, let's discuss a little bit about the loss function here. So loss function will be, as we have discussed, the CrossEntropy loss, and this loss function is a very simple loss function. Like it takes an input, the prediction, which will be here the output, and as you can remember, the prediction is of shape 16 by 3. Okay, so this is a matrix, batch size multiplied by the labels, and the output will be a one-dimensional vector. So it takes two inputs, one is a matrix and one is a tensor. And for example, let's make this the label, the true label. Like I can define it here, y equal wild argmax, okay, and give it the y. So as you can see here, it is 0.6551. Although it is the maximum of the indices, but the output here, they are different numbers. Okay, so these are probabilities you can see. And what does the CrossEntropy do internally? it does this log softmax, and then it applies this entropy calculation after that. So we don't need here to add, for example, nn log softmax. We don't add it here, okay? Because the CrossEntropy do it internally for us. And from the documentation, it says that it takes the raw input without any without any transformation of the linear layer output. So we need to give it this linear layer as it is and just apply it in that way. And this is the loss value that will be the gradient will be calculated across this. Okay. So also another point here, while evaluating, there will be no gradient because we need to predict. So the gradient will be needed only while doing the training. So while training here, we need to have this gradient and we need to activate these many different layers. But while evaluating, we need to calculate the predictions only without any gradient, because the gradient takes a lot of time if I have a large huge model like Barrett GPT or something like this. So gradient will be taking much more time, and in the evaluating mode I need to disable or calculate the prediction without any gradient. So we need to take care of this part. So let's start using this train function. I have here to activate all the model layers. So this will be model.train. So now this is the training mode. After this, I will be creating an epoch loss variable, which will be of 0. And then here I will be fetching our batches. So like this will be the input and output, and this will be batch, would be a dictionary as you have seen before. Regarding I remember we have seen this output, it was trained batches, I remember, and this will be next of answer. Okay, so I need to fetch this input and this output. Okay, this will be the tensor, and this will be another tensor as the true label. Okay, so I need to fetch this input and fetch that output. Okay, the forward propagation will be I can call it this label, and here I can call it this out. Model will be taking in the input, of course. Okay, model will be taking in the input of our data and predicting this output. Now we calculate the loss. Basically, it is nothing but using this backward function. Okay, sorry for that. It will be first we need to calculate the loss, so it will be using this loss function as we have calculated it here. It takes this prediction. So what is the prediction here? It is out and the label. Okay, so for now we have done the forward propagation. This is the forward propagation, and this is the loss calculation. Then we need to go through the backward propagation. So first thing here, we need to clean the gradient. So basically, we need to remove any accumulated gradient from the previous batches and make it 0 grad. Okay, so we need to use the optimizer here, and as you can say, like it will be zero grad method to clean all the previous gradients that been calculated through previous patches. What I need from previous patches, I need only to optimize the model parameters. Okay, so each patch gives me a new information, so I don't need to accumulate multiple information while making the new, while taking the information from the new patch. Okay, because the information is nothing but directions of the vectors, so I don't need to accumulate these values across each other. So I need to first zero this, remove the previous patches values, and then we need to go to make this backward propagation. So this will be using this loss. Okay, and then we need to adjust our model parameters here. As we can say, we need to make a step into the opposite direction of the gradient calculation. Okay, then we need to accumulate the epoch loss in order to calculate the loss and see how it progress across each epoch. Epoch loss dot, I need to actually take the scalar value of it, not the tensor, because for example, if I have a tensor here, like this will be, I call it L. So I don't need this tensor 016, I need only this 01655. So I have this function which called item that returns it as a scalar integer. Okay, so I call item here, and after this loop I will be returning this epoch loss. Okay, so here is the forward propagation, here is the loss calculation, and this is the 3 steps for backward propagation that PyTorch makes. Zero grad will be removing any gradient from the previous steps. Loss backward, it accumulates the gradients. Okay, and then we have this optimizer. So the optimizer here, I can make it every batch. I can update the optimizer every batch, or I can update or make the step, for example, every 5 patches. Why is that? Because what is the main objective if I have the whole dataset to be inserted to the model, and the whole dataset being calculating this backward propagation and this x inverse by x by this mathematical equation? I need, this is the normal equation, which is the optimal case, that I can insert the whole dataset into the model and calculate this backward propagation. But due to the huge size of data and the low resources with RAMs, so I need to break it into batches and calculate this gradient for each batch. So what if I can make these gradient calculations not for each step, because each step doesn't give the whole picture or the whole objective of this data, but it gives a part of the information, not the whole information. So I can, for example, here make the optimizer step if each 2 steps, each 3 batches, I can update the optimizer. It's sometimes it's some tricks that can be enabled. So PyTorch is a very flexible library framework, as you can see. So also there exists another framework which called PyTorch Lightning, which will be discovering by the next set of lectures, but after mastering this Torch framework first. Okay, So next part will be the evaluation function. So basically it's nothing but will be the same part here. I will be taking these three lines as this will be duplicated, but as we have said, like we need first to change the mode of the model into eval and looping through these patches as is, and also calculating this epoch loss. Okay, and also calculating this loss function. Okay, and then we need to take this epoch loss, be calculated. So now the model will be in the eval mode. So we will be dropping this dropout layer and dropping this patch normalization layer in this mode. We will not be needing them. We will not need them in this mode. And but also we need to do another thing. We need to deactivate the gradient. So we need to use this with torch dot no grad. Okay. So this will be disabling the gradients while we are, this is the context, will be inside this context, will be not, will be avoiding, will be avoid calculating any gradients regarding this forward propagation in this propagating of these tensors. Okay. Also here takes those functions a model, and of course we don't need this optimizer because we don't train anything here. Okay. Now let's run it, and then let's go to the final part, which is the configs. I didn't make it as a class because we don't need to make it a class here inside the notebook. Basically, we are here defining the learning rate. It's hyperparameters. All of these are hyperparameters. I can change, and also the loss function might be changed if you need. Can be mean square error if you would like, but it's of course in the classification part we need the CrossEntropy and or binary CrossEntropy. Like if it was two labels only, we have this PCE loss. Okay, but CrossEntropy for multiple classes. And then using these hyperparameters, the number of epochs I need to train the model, the batch size, I make it 5. It's a very small, like the model can underfit here, but I need to show you the main idea. Okay, now the input and output dimension, of course, you have 4 features and 3 labels, classes. The IrisNet will be taking these two parameters. And after this, we will be giving our model to the optimizer. The optimizer here, as we have discussed, it is the Adam with weight decay, which is the modified version of the of Adam optimizer. It's a pretty popular optimizer. We can also use multiple optimizers. For example, this SGD, or like you can try different optimizers, as you can see. Also, you might be better learning them because it is very good to know the theory before you apply. Okay, so let's define this, and then we will be having this data preparation. I will be here test splitting our dataset, and we'll be generating datasets, then we'll be generating data loaders. So this will be the splitting of our whole dataset into training and evaluation. And make sure that your train DF and eval DF contains the 3 labels, because sometimes if the data is too small, you might be splitting the dataset without having all the labels in the training. So the model never seen this label before, so it will never predict it. Okay, so keep and but for of course in the large dataset you have this you can be more safe regarding splitting the dataset in that way. Okay, and the output here, of course, the dataset, as we have discussed, it takes two input. It takes only one. Oh, sorry. It takes only one input. It is the train, the frame. Okay, and then I have done this reset index because it sometimes shuffles the data. So while loading it, it might be having this indexing error. So I need to reset the index in order to reorder them in the numerical level. Okay, so I have this train dataset and eval dataset. It will be the input of the data loader, and I can here define the batch size and also the number of workers. If you have a GPU or something, like it can be processing the data, multiple workers can move the data from the RAM of the GPU into the GPU processing unit and applying this processing of the linear layers or whatever you have developed inside your model module, and then pre-processing this dataset in parallel. So if you have defined, for example, 4 workers, so like you can imagine 4 persons taking the data from the RAM, putting it to the GPU, processing it, and giving back the model parameter modification. Okay, but we don't need this parameter because we are training on CPU. So you can make it worker as 0. And the training loop here, as you can see, it will be for a range of epochs that we have defined before. It's 5 epochs. We will be training this function, calling the train function and the eval function. But here we just don't have accuracy. Okay, I can remove it from here also. Actually, you can make it from your side. You can try to create how to write the accuracy, how to calculate the accuracy of each batch. Okay, I will make this as an assignment for your side. So let's run it. Okay, so what is the first error here? Epoch loss.item int object is not attribute item. So let's check it. Okay, yeah, I remember I have renamed it again. It is loss.item, not epoch loss.item. Okay, let's redefine it again and training it. Okay, of course it's pretty fast and it calculates the loss, and this is the whole summation of the loss across the whole patches. Okay, I hope you understand these main concepts of PyTorch. It's pretty simple. Like all you need is like you can work on again or watch as a video again, but I need you to be pretty confident of what is each module do. So the model will be defining the layers, whatever you need. The engine, the dataset will be any pre-processing to the data. The train.by it, whatever we have done in the latter cells in the notebook, we will be duping, will be defining the model and the optimizer, will be defining the data loader, pre-processing the test and splitting the dataset. The engine will be just calling the train, eval, and test. We didn't do the test, but the test will be the same as eval, but it will take another patch. We need to patch also the train dataset again to make it in eval, and that final dataset will be in test. The configs will be as a number of epochs, and the utilization, we didn't have much utilization function, but we can, for example, move this into an utilization function as you like. Okay, so I hope you have understand the main idea of the PyTorch template, and next lecture we will be having the food review or the GRU, LSTM, and RNN's neural networks, recurrent neural networks, to understand how they works in details. So keep tuned and thank you.